Hello everyone, it's Homer White back again with the part 2 of our video lectures on the third data analysis report. So this time we're going to look at specifics about R Markdown or R that helped us to produce this particular report. The R Markdown document itself is homework 03 example.rmd that you may find in the appropriate place in the common source folder for the course. And we also have the Word document available, and we'll be going back and forth between the two. One thing I'd like to point out initially is that we listed out the first 12 rows of the original data frame lizard sprint using the head function. That's a handy function that can give you the first number of rows that you specify. All you have to provide to it is the argument. All you have to provide to it is two arguments. First of all, the data frame itself, lizard sprint, and then of course a comma. The second argument is a number specifying how many of the first rows that you would like to see. We also did some data manipulation, replacing the original lizard sprint data frame with a new one that was going to be more amenable to the type of data analysis we want to do. And I'd like to show you the R techniques that are involved in that. So here we are in the original R Markdown document, and here's the sequence of commands that gave us the new data frame. So how did they work? First of all, I need to talk to you a little bit about how lizard sprint looks. This is a view of the original lizard sprint data frame, and as you recall, every odd number row gave you an initial speed for a lizard. So the first row gave you the initial speed for lizard number 1. The third row gives you an initial speed for lizard number 2. The fifth row gives you an initial speed for lizard number 3, and so on. Every even number row gives you the speed for a lizard 1 year later. Thus, the second row gives you the speed for lizard number 1 after 1 year. The fourth row gives you the speed for lizard number 2 after 1 year, and so on. Ultimately, what we would like to do is pick up all of the odd number rows for speed and make one variable out of them. Those will be the speeds before. We also want to pick up the even numbered rows for the speeds, put them together, and make them the speed 1 year later, thus creating two separate variables out of one column. So how do we go about this? It's a multi-step process. Looking back at the code, it appears that we construct the initial speeds, which we're going to call the variable first, by doing some kind of selection from the data frame lizard sprint. The way you do selection from a data frame is to use matching brackets, opening and closing brackets. Let me do a simple selection down here in the console. Lizard sprint, brackets, 4, 2. What this is going to produce is the number that's in the fourth row and second column of the data frame lizard sprint. 1.3. Is that for real? Let's check. Sure enough, fourth row, second column is a 1.30. So when you use the brackets for selection, what comes before the column refers to rows. What comes after the comma refers to columns. In our previous example, we selected 1 row, 1 column, thus getting 1 element. It's possible, however, to select more than 1 row at a time, or more than 1 column at a time, if you like. Consider the following example. Lizard sprint, brackets, concatenation, 1, 2, 5. After that, a comma, and then 2. This will select the first, second, and fifth rows, but only the second column from each of those rows. Running the command, we have the numbers 1.43, 1.37, and 1.64. Looking up in our view Sure enough, that's the second column, first, second, and fifth rows. Looking more closely back at our R code within the R Markdown document, we see that what comes before the comma is actually a sequence function. Let's try this sequence function just by itself. So I'll copy it, paste it into the console, and run it. Notice that I get all the odd numbers from 1 through 67. That makes sense. I made a sequence beginning at 1, ending at 67, going up by 2 each time. So what I'm doing is selecting all of the odd-numbered rows in the data frame lizard sprint and restricting myself to the second column of them. That's going to give me all of the speeds in odd-numbered rows. Those are the initial speeds. If I were to select and then run the entire phrase, lizard sprint, sequence 1 through 67 by 2, comma, second column, then again, I should get all of the initial speeds. There they are. It's those initial speeds that are being put into the object first. As for the object second, what's in it is all of the final speeds. We can tell that because the rows that are being selected are the even-numbered rows. The rows from 2 to 68 going up by 2. And again, the columns being selected are just the second column. So now we have two objects that are in our global environment if we were to run both of these commands. Let me go ahead and run them. If you were to look over into your environment, you'll see that first and second are now present in your global environment. Both of them are numerical vectors that contain 34 items each. I can combine both of them together into a data frame by using the data.frame function. The arguments of the function are the objects I'd like to combine, the first and the second. So if I were to run just data frame, first comma second, I should get a printout of this data frame in the console. Let's give it a try. Yes, there it is. The whole data frame that I'd like to build. Of course, I don't want it to go out to the console. I'd like it to be stored in an object that I can refer to later. And so I store it in the object lizards. So if I were to run this third command, then lizards will show up as a data frame in my global environment. Sure enough, there it is. Once I have this new data frame, I'll go ahead and view it. This is what I can more easily work on. I can compute differences between second speeds and first speeds and do a kind of analysis that we already know how to do with repeated measure studies. Another thing that you saw done in the data analysis report was the construction of the differences in the speeds and the addition of these speed differences to the data frame lizards. Let's see how that was done. The R code is shown in the report itself because we think that might be of interest to the reader. Let's go back to the R Markdown document and see it in action. Here we see the code chunk. It started with the command with. With lizards, we're going to do second minus first. Second and first are variables that occur in the data frame lizards. The command with says, make sure that you look in the data frame lizards in order to find the variables that I'm going to talk to you about next. That way, R knows to look inside of lizards to find second and first. What does it do with them? It subtracts them. It subtracts the first speed from the second speed for each row in the data frame. If I were to run just this command, then I would get the 34 differences down in the console. There they are. But what I'm going to do is store them in a new variable. And I want that variable to be an additional variable, an added column to the data frame lizards. The way that's done is by storing it in lizards $, and then the name of the variable, which I would like to be speakdiff. So if I were to run this command, nothing would show up in the console's output. But when we look back at lizards, we'll find that now it's got 34 rows and 3 columns. We have now a third column, speeddiff. Another possibly interesting feature of this data analysis report was a little bit more fancy math notation. In the statement of the hypotheses, notice that the null hypothesis and the alternative hypothesis are italicized. They look like mathematical symbols, and they have subscripts. We also appear to have found a way to write a not equal sign. Now, you don't have to use math notation in your own reports, but if you're interested in learning how to do it, it's really not hard, and it's kind of fun. So let's see how it's done. As we've seen in previous reports, we can make math by using a pair of enclosing $signs. So here's a statement of the null hypothesis in the R Markdown document. The subscript of 0 for the null hypothesis is gotten with that underscore. Here's the colon you saw after the null hypothesis symbol. We've already seen how to make a mu with a backslash and then the mu. It had a subscript d, so here's the underscore and then the d. So that's how we got the null hypothesis. The alternative hypothesis is gotten the same way, except we needed a not equal sign. There's lots of ways to get special math symbols, and the way to get a not equal sign is simply a backslash NEQ. If you'd like to learn more about making math with R Markdown, you'll need to learn about a markup language called LaTeX, and there's a lot of tutorials about that on the web, and you can see me to learn more about it. Another feature that was new to this data report, and probably won't occur in the data report that you have assigned to you, but which may occur to you in your future life, is the working with percentages. So let's take a look at the conclusion, where we got interested in seeing what was the biggest percent change in speed that according to the data might be considered a reasonable possible value for the population out there. We decided to compute this by looking at the largest change that lay inside of our confidence interval. And in terms of size, the largest change turned out to be the lower bound of the confidence interval, the minus 0.19 meters per second. What we want to do is compare that 0.19 with the average speed initially for the lizards. So in terms of our code, we found the mean of the first speeds from the data frame lizards, stored it in an object called firstMean, and printed it out for the reader. So on average, the lizards were sprinting at a rate of 2.183 meters per second at the beginning of the study. Since the change was negative 0.19 meters per second, to find the percentage change, you'll need to divide the minus 0.19 by the mean of the first speeds, and then multiply by 100 to get a percent. So that's how we got our minus 8.7% decrease. That was the largest possible decrease that actually occurred within the confidence interval itself. It's certainly not our best or our first guess as to what the actual percentage for the population was. That was more like a minus 2.6%. Thank you for listening.